Hello, good morning, everyone. I want to welcome you to another statistical learning class. Give me 1 second. Just 1 second. Okay, so before I get started today, we've completed the makeup last night, and of course, I'm actually going to watch the recordings because when you join, um, it's automatically recording you. So I really want to see if you follow the instruction. The grade that you have right now is not your final grade because I'm actually going to watch the recording to make sure you follow the instruction. Okay. So let me come. Okay, so once again, I want to welcome you. Please pay attention. Pay attention. Those of you at the back, can you hear me? Okay, thank you so much. The other time I introduced you to probabilistic or graphical model, and of course I remember I mentioned the benefits of using the probabilistic or graphical model. The probabilistic graphical model is also a dimensionality reduction technique like MDS or like principal component analysis, but with probabilistic graphical model, we're able to represent high dimensional data in a compact way. And of course, you know, I remember I said we actually use the idea of probability theory and a graph theory because the graphical structure became necessary because we are looking for a compact way of representing our data set. And of course, the probability theory enable us to answer probabilistic queries. Of course, I think I've mentioned, the significance of, probabilistic or graphical model. Now, we have different types of probabilistic or graphical model. What we want to talk about today that we call Bayesian network is one of the types of probabilistic or graphical model. And let me tell you this, today, I'm actually going to show you uh, area of application. Let me tell you this. Because of the fact that we live in a stochastic environment, the world is probability space, and whether from medical you know maybe medical areas to weather prediction, even to the law practice, we can apply probabilistic or graphical model. So I'm going to show you application today, okay, of probabilistic graphical model, okay, because in all these areas uncertainty is involved. And of course, probability theory is also going to take a center stage. So I'm going to show you how we can use probabilistic graphical model in the court of law, in medical diagnosis, in weather prediction, in supply chain, and so on like that. So in the outline, and that was why I put probabilistic graphical models in real life, then computational example. But you know what? I need you to pay attention. I'm going to start. Take a look at this. You wake up in the morning and you find out that your grass is wet. Okay. Now, your grass is that is wet could be attributed to two scenarios. It could be that maybe there was event of rain or the sprinkler is navigated. And let me also say that the sprinkler also depends on the rain. So if you take a look at what I'm having here, the parent is rain. Now, if you take a look at what I have here, I want to figure out what is the joint probability of having a sprinkler navigated the rain and the grass wet. And if I actually want to do that, I'm actually going to use the idea of a probabilistic graphical structure. If you take a look at this guy is a node S. Okay, this is R, rain, and this is G. Okay, now if I want to figure out the joint probability, okay, it's actually going to be the probability of rain. You can see rain does not have a parent. According to this structure, it doesn't have a parent. Okay, and that's why it's not conditioned on any event. Now, if you take a look at for sprinkler, you can see an arrow. Arrow go from rain to sprinkler means the rain causes the event of sprinkler. Okay, that's why you see here S given R. And when you take a look at the grass wet actually have two arrows, one arrow from sprinkler, the other arrow from the rain. And take a look at that. And that's why we have the probability of a G given S and R. Okay, so this is what we call a factorization. Okay, the probabilistic graphical model enable us to factor, to represent the joint probability of having a sprinkler or the rain and the grass wet as that. Now, let me tell you this. If all these events are absolutely independent, I'm going to say that again. If all these events are absolutely independent, this guy, we're only going to have three parameters. This guy is only going to be equal to the P of S, okay, the P of R, the P of R, and the P of G. Okay, please pay attention. Okay, if all the three events are absolute independent, we're actually going to have the product of the marginal. Okay, I just wanted to take note of that. And let me also tell you this. Because we know that events are not likely going to be independent, I want to prove to you that with the use of probabilistic graphical model, we are able to say parameter in a parameter space. Now, the sprinkler here is binary. Rain is binary. Grass wet is binary. What do I mean by binary? He said that the sprinkler is on or off. He said that he said that there's event of rain or not. It's either the grass is wet or not. That's what we mean by binary. Each of these variables having two states. Now, our situation where we want to use the conventional method, the number of parameters that we're going to estimate will be 2 raised to power 3 minus 1. Please pay attention. 2 raised to power 3 minus 1. Okay, that would be 7. It means we need 7 parameters to be estimated if all these events are independent, if they are not independent, and we do not want to represent them using a graphical structure. I'm going to say this again. If events are not independent, I'm going to say that again. If events are not independent, and each event has two possible states, it should be 2 raised to power 3 minus 1 to know the number of parameters needed. But I want to tell you, using a graphical structure, the number of parameters will be less than 2 raised to power 3 minus 1. Imagine I have 10 variables, and each of them has two states. That would be 2 raised to power 10 minus 1. If if we don't want to use graphical structure. But with the use of graphical structure, we're never going to have up to that number of parameters. Okay, now do you know, based on this now, I can answer inference question. I want to find what is the probability that the grass is wet. Please pay attention. If you don't understand, ask me question. Okay? If you don't understand, ask me question. Now, I want to find the probability that the grass is wet, but I already know this from the structure. I know this from the structure. I know the joint from the graphical structure, but I want to figure out the probability that the grass is wet. If I want to do that, I'm actually going to sum the joint with respect to the variable I'm not interested in. I'm not interested in rain. I'm not interested in sprinkler. I'm only interested in the event of grass is wet. So what I'm going to do, I'm actually going to sum the joint with respect to the variable I'm not interested in. And you know what? Do you know that this guy here, this guy, is the same thing as this guy according to the structure? That's why according to the structure, okay, is the same thing as that guy. So all what I'm just going to do is to sum that with respect to that. Now, you know what I'm doing now? I'm actually having probabilistic queries. I'm answering probabilistic questions. Now, I can also find what is the probability of a grass is wet, okay, conditionally on rain. What is the probability that my grass that is wet is as a result of a rain? Okay, I can also figure it out. If I want to figure it out, it means I'm not interested in sprinkler. Okay, I know event of rain and when sprinkler is navigated could lead to grass wet, but I'm not interested in sprinkler right now. Then you know what I'm going to do? I'm actually going to sum that with respect to the variable I'm not interested in. And because of that, I'm actually going to have this. Now, I want to go into, please pay attention. I want to go into medical example now. Okay. And the focus here is on COVID-19. Okay. Now, the COVID-19 is believed to have a probabilistic relationship with other variables. COVID-19 has a relationship with influenza B. It has relationship with the platelet. If you take a look at this, the platelets count, you can see the arrow go from the platelet count to the COVID-19, which means probabilistically relationship exists. We're trying to say the platelet count can also lead to the event of COVID-19. Take a look at this coronavirus HKUI, okay, also lead to that lead to that. And let me tell you this, when somebody has a COVID-19, it's either the person is admitted into hospital, into regular ward, or here, take a look at that. And we also have other diseases that also go into the ward. Take a look at that. Now, how do I get the graphical structure here? This graphical structure was actually put into, they were actually put in place according to domain expert knowledge. Those who understand, okay, the relationship between other variables and COVID-19. Now, do you know that based on this, what if I give you this in exam and I ask you the probability of the joint occurrence of all the events? I can give you this in exam. Right? How many node do I have? I got let me count them. How many node? 1, 2, 3, 4, 5, 6, 7, 8. I can ask you, what is the probability of the joint occurrence? Okay, I expect you to make use of the way you figure this out. The way you figure, here I only have 3 nodes. I only have 3 events. Okay, the way you figure this out, I can also ask you to figure this out. Okay, so if we have data set now, we can actually use Bayesian network, as a probabilistic measure for COVID-19. Okay, we use that in diagnosis. Okay, now I'm going to go into another example now. Okay, please pay attention. Okay, pay attention. I want to talk about the diagnosis of lung disease. And of course, the experts in this area has provided us with a graphical structure. And you know what? For each node, we have a node, smokes. Okay, we're trying to say here, lung disease, the parent of lung disease is smokes. You can see the arrow. And the lung disease, okay, it's a parent to shortness of breath, chest pain, and cough. Okay, and if you take a look at the code here, cold is a parent to cough, and cold is a parent to fever. But there's something I need you to see. Okay, so, uh, we could have situation where event could have two parents. Take a look at the cough. Somebody who have a lung disease could actually going to have a cough. Somebody who have a cold also going to have a cough, and that's why doctors, they actually need to go beyond ways of figuring things out at times, and that is why the use of probability is going to come into play, because the situation where you are seeing somebody who have different diseases having the same symptoms. Okay, so if you take a look at what I have here, this is the structure provided. If I want to figure out the probability of lung disease, putting into consideration the probabilistic dependencies or the probabilistic relationship with other variables, I can figure it out. Now there's something I needed to say. Take a look at this. Smokes. Here I have smoke is a node. This is another node. This is another node. How many nodes do we have altogether? 1, 2, 3, 4, 5, 6, 7. We have a 7 node, and each of these node is binary. Binary. Binary means they have two states. Let's start with the smokes. It's either somebody smoke or not. Take a look at this. This guy is trying to say 20% smoke, 80% do not. Maybe based on the data that we have, based on medical data we have in a particular clinic. And I wanted to look at the lung disease here. The lung disease depends on smoke, right? If I'm going to create a table for that, I'm actually going to have that table will connect smokes and lung disease. Where here, this guy is going to say 10% of those who smoke do not have a lung disease. And this guy is going to say 89% of those who smoke, okay, do not have a lung disease. And, 10% of those who smoke have lung disease. If you take a look at what I have here, okay, each of these table is called conditional probability table. Conditional probability table. We figure each of these out from the data set that we have. Now take a look at this code. It's either somebody is code or not. 2% code, 98% no code. Take a look at that. And when you take a look at the fever here depend on code. And that's why if you take a look at the table, you're actually going to see a contingency or a cross tabulation between a code and fever. So, if you want to take this to the next, if you want to take this to the next direction, we can actually use this information here to figure out the probability of a patient having lung disease, putting into consideration the probabilistic relationship between having lung disease and some other medical variables. Okay, now I need you to pay attention to this guy. Cough has two parents. One is cold, one is lung disease. And you know what? This having two levels, this having two levels, this having two levels, 2 times 2 times 2, that would be 8. That's why here the number of cells here is 8. Did you see that? The number of cells here is 8. That's why you see this 8. Because here I'm actually going to consider cough, cold, and lung disease. That's what you're seeing here. Take a look at that. Now, I want to move to supply chain. The graphical structure, the probabilistic graphical structure are also very useful in supply chain. If you take a look at what I have here, it's trying to say when there's a global disruption, when there's economic collapse could actually cause the events to, actually going to cause this event. Okay, supply one, it affects supply one, supply two, and supply three. I wanted to take a look at that. If there's a global disruption, okay, you can see the arrow starting from here, going to supply one, going to supply two, okay, supplier two, going to supplier three. And not only that, when there's a local disruption, when I say local disruption, maybe I'm talking about the labor strike, the flood, fire, tsunami, earthquake, and tornado also going to affect suppliers. So what we're trying to say here, okay, whether there's a global disruption or a local disruption, actually going to affect supply chain. It's going to affect supplier one, supplier two, and supplier three. If I actually want to answer a question now here, a probabilistic question. Of course, the idea of probabilistic graphical model can actually be used. Now, I want to go into criminal justice system. Please pay attention. I want to go into criminal justice system. Let me tell you this. Statistics is a fantastic course because what we do in statistics cuts across all areas. Today, I've walked you through the significance of probabilistic graphical model in medical diagnosis, and I've also talked about supply chain, but right now I'm in a criminal justice system. Now, let me tell you this. Take a look at this structure. This particular graphical structure was actually put in place by an expert in the legal system. Okay, now I need you to pay attention to this: juvenile felony and juvenile misdemeanor. Okay, I want to believe this is the two of them here. They are the kind of offenses committed by a child. One is serious, the other one is not. Okay, now we believe that if a child have history of, according to the legal experts, if a child have history of conviction, there is possibility when turning adults. There's possibility. Okay, I'm not saying all, because there's possibility. It's either somebody, when by the time he turn adult, is going to change, is not going to have conviction, or there's also possibility that it's also going to be charged. It's also going to. So if you take a look at this, prior convictions, prior convictions. When I say prior convictions, I mean the conviction as adults depend on juvenile felony, also depend on juvenile, misdemeanor. Okay, and the current type of crime, maybe somebody's accused right now as an adult. The type of crime also depends on, the crime as a child. That's why you see here the parent of the type of crime is actually juvenile, and the two juvenile. Okay, now what is this guy? Here I want to talk about recidivism. What do we mean by recidivism? In the court of law, okay, when an accused person is being tried, and if the courts already established the fact that he committed the offense before sentencing, before sentencing, they normally put into consideration some factors. Has anybody heard about aggravating factors? Okay, they normally put into consideration some factors, and recidivate means what is the probability that this person will not commit offense again? Because before they can actually decide on the bail or condition, before they could take decision on bail, or before they could take decision on sentencing, or before they could take decision on parole. Has anybody heard about parole? Okay, before they could take decision on that, they really will have to put into consideration some factors. So recidivate means what is the probability that an accused person, this guy, okay, that has been established by the court that is guilty, will not reoffend. Okay, and because of that, they use what we call compass. Compass, C in compass, actually mean correctional, is who means offenders, M means management, or P means profiling. Okay, profiling for A means alternative, and S means sanctions. Okay, now this compass system is being used to decide. Compass system is being used to decide whether somebody who has been committed of an offense will reoffense or not. Okay, I think I can identify 4 states in the United States that use a compass system and jurisdiction. Okay, Wisconsin use that, Florida use that, New York use that, and California use that. But let me tell you this: there's something with the compass. Compass is very controversial. Controversial in the sense that at times, because the network is probabilistic, and the network uses the fact that past events predict the future event, and there's possibility that compass system may actually penalize a certain group. I'm going to say that again. The compass system may penalize a certain groups because this architecture rely on, past event, assumption that past event predicts the future event. And that is the reason why this is being controversial. Okay. But based on what I have right now, if I want you to write the probability of the joint occurrence of all of this is going to be that. Take a look at that. Okay. When I'm going to start, I'm actually going to start, please pay attention, with the two parents. These are the parents, right? They don't depend on anything. These are the parents. Can you see that? This is it. Take a look at that. Can you see that? These are the parents. What is the next one? The next one is type of crime. Type of crime depend on the two juvenile, and that's why you see here the type of crime. Can you see that? The probability of the crime depending on the two juvenile. And not only that, if I want to go to this guy also depend on the two juvenile. Okay, that's what you're seeing here. Okay, and finally, if you take a look at this guy only depend on the type on on the current type of crime and the history of conviction as adults. Now, this is what I'm trying to say. It means this guy, this guy, and this guy, they are conditionally independent. If I have observed this guy, if I have observed your current type of crime, oh, sorry, not you, not you. If I have observed this guy current type of crime, okay, and the prior conviction, okay, now that is enough to give me information about whether he's going to commit the crime again or not. That's, the juvenile, what he did as a child, the offense that he committed as a child does not give us information. And that is what I mean by conditional independence. So it means what I'm trying to say here is that this guy and this guy, they are conditionally independent, given that we have observed this guy. If I have observed the current crime, or the current type of crime of the defendant, and I've also put into consideration the prior conviction as an adult, okay, if I want to figure out whether it's going to reoffend or not, that doesn't, the juvenile, the offense as a child is expected not to give any information. And that's what we mean by conditional independent. Okay. Now I want to move right now. I want to move to this. That was a celebrated case in the United States around 1994. Has anybody had about O.J. Simpson? Okay. Thank you so much. Simpson was tried. I think they found somebody murdered. And that guy, that lady happens to be his former wife. But the fact that O.J. Simpson has history of domestic abuse, it was actually linked to the murder. But you know what? As at that time in Los Angeles, um, you know, people in Los Angeles, a particular race in Los Angeles at the time, they believed that O.J. Simpson did not commit a crime. It was LAPD that framed up O.J. Simpson. Now, I wanted to take a look at what I have here. Let me tell you this. In the court of law, the probabilistic graphical model can actually be used to model hypothesis. The hypothesis is maybe somebody was alleged, somebody was killed here, and they say, oh, Simpson killed this person. And another hypothesis here is that the LAPD frame up Simpson, and we're also going to have some evidences in terms of the blood stain. If you take a look at the blue one, please pay attention. If you take a look at the blue node are the hypothesis. Okay, the blue node are the hypothesis. Okay, Simpson killed, Simpson was abusive. It's an hypothesis. They need to prove that before the court of law. Okay, Simpson killed Brown. It's an hypothesis that need to be, then the drug related, because let me tell you this, in the court of law, they have hypothesis, they have hypothesis, they have evidence, and they also have alternative cause. Okay, the alternative cause provided is that, oh, maybe somebody that died, her death was drug related. And another alternative, is that, oh, the LAPD framed Simpson. But there's something I needed to say. Please pay attention. Now, if this hypothesis is true, this is the consequence of the hypothesis. I needed to pay attention to that. If Simpson actually is abusive as claimed, okay, then the evidence, that will lead to expected evidence that Simpson beats Brown. Okay. Now, if Simpson killed Brown, okay, what would be the consequence of that? The consequence of the killing is actually is the evidences that they saw at the scene. Okay. Now I needed to see the Simpson killed Brown. Okay. The blood sock, the blood stain, the hand gloves, the blood at the scene. So the consequence of the killing, okay, so which means here the note kill is actually the parent. I wanted to take a look at that. And there's also a possibility that LAPD could also frame, if it is true that LAPD frames Simpson, then there's possibility of having fake evidences. Okay, fake piece of evidence. That's why you see that. Now, this particular probabilistic graphical model was actually drawn by an expert. And we can actually use this to answer probability query. What is the probability that Simpson was responsible given the evidence? We can figure that out using the probabilistic graphical structure. I want to move away from that. I want to go to weather now. Some of you when you listen to news and they're going to tell you, oh, tomorrow there's possibility of rain. Oh, there's possibility of snow. But you know what? We can also represent that by a graphical structure. I needed to pay attention now. Okay. Now, the humidity at 3 p.m. depend on the humidity at 9 a.m. And humidity at 3 p.m. will determine whether there's a rain tomorrow. And not only that, it is not only humidity at 3 p.m. that determines whether there's going to be a rain tomorrow. The wind speed also determines that. Okay. So if you take a look at what I have, for each of these, I have a probability, a conditional probability table. Okay. If you take a look at this, okay, humidity at 9 a.m. Okay. At 9 a.m., less than 60, it happens 30% of the time. Humidity, greater than 60 at 9 a.m. occur at 69% of the time. Okay. If you take a look at that. Now, the humidity at 3 p.m. depend on the humidity at 9 a.m. I'm actually going to have 4 cells because humidity at 9 a.m. is binary 2. Humidity at 3 p.m. also 2 times 2 is 4. And that's why I have that cells. Okay. Now, the wind speed has 3. It's not binary. It could be less than 40. It could be 40 to 50. It could be greater than 50. Can you see what I have? And let me also tell you this. You can see the arrow from the wind speed to rainfall. So another arrow is coming from humidity at 3 p.m. to rainfall. Okay, so if if you take a look at humidity at 3 p.m., how many cells do we have here? We got 4, right? Okay, if you look at the wind speed, how many cells do we have? We got 3. Now, if I want to form the rain, since the 2 of them are faded, what is 4 times 3? 12. And that is why you're actually going to see 12. Do you see that? Is there any question on this? Is there any question on that? So go ahead.
No, and then the humidity is 2 6, so wouldn't it be 2 2 3 rather than 4 3?
Okay, I'm going to explain that. Please pay attention. Here, how many states? 2, because of that, right? Here, how many states? 3, because of this. Now, if you Humidity at 3 p.m. and humidity at 9 a.m., they are having two states. But because humidity at 3 p.m., can you see the arrow? Depend on humidity at 9 a.m., then what is 2 times 2? That is why we have this guy. How many do we have inside? 4. Does that make sense now? Now, I want to talk about rain now. I want to talk about rain now. And 2 arrows come to rain. Okay? This arrow that come to rain, how many do you have here? Because this is 4, right? Right? Now, how many do we have here? This is 3, right? Now, this rain, okay, 2 arrow comes to the rain, the one from the humidity at 3 p.m. and the one from, and don't forget, humidity at 3 p.m. also, as a mother, as a parent, and that is why here, if you multiply 4 by 3, that will be 12. Now, if you take a look at what I have here, if you count the cells, that will give you 12. So which means rain, you've put into consideration everything. If you take a look at this now, you can talk about humidity at 3 p.m. and you can talk about other variables. So that is why you have the 6, you have the 12. So here, I'm trying to say this is actually giving you already a prediction that this is they can actually say, okay, when the humidity at 3 p.m. is that, okay, and the wind speed is that, and that is that, they're actually going to have that guy. So this is how they normally give us a prediction of certain percent, that you know what I mean. They study the situation. So what I'm trying to say here, the probabilistic graphical model also very useful in weather prediction. Let's take a look at this. This is where computation, you know, let me tell you this. Uh, it's not because I have 15 minutes to teach, okay? Explaining this in class may take forever. I have a video on this that I'm actually going to share with you. And video on the computation, because it's going to take a lot of time, okay? Uh, I'm actually going to share you the video today, okay? For instance, we are given this. Take a look at this. A causes C and B. Can you see the arrow? A causes C, A also causes B, and B causes D. And they've given you this. Please pay attention. They've given you, they've given you this, they've given you this, they've given you that, they've given you that. Okay. Now, if you look at what they've given you, they've given you C giving A, because C is coming from A. Look at the arrow. Okay. When C is coming from A, it could be A, and if A is either A is true or A is false. That's why you see that. But I wanted to see something. A itself is this. Of course, what would be the A complement? If probability of A equal to zero point 0.4, the probability of A complement would be 0.6. Okay. Now, if you look at B, you look at the arrow, you look at B is coming from A, and that's why you see the conditional probability of B giving A. I'm just trying to explain what the conditional probability table they give you right now. And also look at D. D depend on B, right? And that is why the conditional probability table is like that. But you know what? In the video that I'm actually going to release, they're going to ask you to find the probability of something using this information here. Okay. And I will advise you watch the video. I'm going to post that video that explain computation today. Okay. I'm also going to post the video as well. I wanted to look at these two graphical structure. When there is burglary, alarm 1 ring, alarm 2 also going to ring. Okay. But the second structure is saying when alarm 1 ring and alarm 2 ring, obviously there's an event of burglary. Please pay attention to these two structures. These two structures are not the same. The first one say if there is event of burglary will cause alarm 1 to ring and alarm 2 to ring. Maybe in your house you have two alarm, okay, that will trigger, when there's maybe infringement of privacy or invasion. Okay. But if you take a look at the second structure cell, the second structure is trying to say alarm one and alarm two, they are independent. And it is only when there is event of burglary that alarm one ring and alarm two also ring. Now, you are given to safeguard your house. You recently installed two different alarm systems by two different reputable manufacturers that use completely different sensors for the alarm system. Which one of the two Bayesian network given below makes independent assumptions that are not true? Please pay attention. Make independent assumptions that are not true. Explain all your reasoning. Okay, as reasoning. Assuming alarm one means that the first alarm system rings, alarm two means that the second alarm system rings, and the burglary means that a burglary is in process. Okay, now I need you to pay attention. I want you to, here I said the second one falsely assume that alarm one and alarm two are independent. I need you to pay attention. Take a look at this. Because that is what he's saying. He said they are independent. He said they are the parent. They don't depend on anything. Okay? But I want to say this. Okay? If you take a look at what I said here, I said, in the answer that I said, the second one, which is this guy here, make an independent assumption that is not realistic. Because you know what happened? Alarm one and alarm two, they are independent if what? If burglary is observed. That's what we call conditional independent. The conditional independent is this guy here. Go ahead. Yeah. Yeah, that's another. Yeah, alarm one, alarm two. The second one is saying they are causing the burglary. But the first one is saying that before you can have alarm one and alarm two triggered, then there must be event of burglary. So that is why the first one is making more sense. Because it is not all graphical structure that make more sense. Okay, it's not all graphical structure that make more sense. Now I can give you some different kind of graphical structure, and I want you to make a sense of that. Okay, so that answer that. Now pay attention now. I think on my time is 10:53. We have 7 more minutes, right? Okay. Now consider the first Bayesian network. That is the first one that makes sense. We consider the first one that makes sense, or we all know the first one makes sense. Alarm one and alarm two only going to ring when there is burglary. Does that make sense? Okay. Now, now consider the first Bayesian network. How many probability need to be specified for its conditional probability tables? I've seen a lot of exam question here. How many probability would need to be given if the same joint probability distribution were specified in a joint probability table? Okay, please pay attention. Okay, and C, okay, they wanted to figure out uh consider the second Bayesian network, assuming we have all this, assuming they gave you all this, they wanted to find the probability of alarm 2 depending on burglary and alarm 1. Like I said, you know, this is the solution here, but you know what I'm going to do? I've made a video that explains this, and I'm going to share you the video. Okay. Even on this example, okay, I've made a video on it. I'm actually going to share you the video. Please make sure you watch the video. For instance, take a look at example 3. Consider the following Bayesian network where F having flu and C coughing. Take a look at this. Okay. Well, of course, when somebody have flu, that person is likely going to cough, right? Now, if they give you this probability of having flu is 0.1. Of course, C depending on F, I'm actually going to have two. I'm going to have the first one. It's either I cough, maybe I cough because of the fact that I have a flu. I can also cough if I don't have a flu. Does that make sense? That's why they give you 2. Take a look at that. Can you see what they give you here? The probability of coughing, given that I have a flu, is 0.8. The probability of coughing, given that I do not have a flu, is 0.3. They gave you that. Okay. And the probability of having a flu is given to be 0.1. The question now says, write down the joint probability table specified by the Bayesian network. Okay. Like I said, I've provided a video where I explain all this extensively. And question B said, determine the probability for the following Bayesian network. What is the probability of C? What is the probability of having a flu given that I cough? What is the probability of having a flu given that I do not cough? All of this, I've made a video on that, extensive video on that, and I want you to watch them. Now, this is another example. Okay, you are given this. They gave you the probability of y to be that, and x depend on y, okay? And they gave you the probability of s given y to be 0.5, probability of s given, this notation means not y, like a complement of y, okay? And they also give you here, and the question is actually saying, we know that x and z are not guaranteed to be independent if the value of y is unknown. Don't forget, if you take a look at this, they are only independent if this is observed. That's a conditional independent. And that's what I said. Okay. Suppose that x and y are not guaranteed to be independent if the value of y is unknown. They can only be independent if the values of y is known. Does that make sense? This means that depending on the probability, s and z can be independent or dependent if the value of y is unknown. Then the question now, construct probability where s and z are independent if the value of y is unknown, and show that they are indeed independent. How am I going to solve all of this? Like I said, I've made an extensive video, and I'm going to share you the video today. I expect you to watch the video. It's very crucial to this course. What am I going to do on Wednesday? We're going to continue, okay, talking about inference in Bayesian network. I'm going to say this again. Please watch the video on computation. And if you watch the video and you don't understand, please meet with me during my office hour. That's all I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
I'm like having a terminal of the little bit life. My life, I'm just the man for the you guys like. You can help to do it.